pronounced Cauchy. And Cauchy did a lot of important things in mathematics. Many of the things he did are more important than the poles and residues idea, but the reason for talking about poles and residues is not particularly to do the problems in 8.4. It's much more that if you take the systems and circuits class in engineering, as you would if you're doing engineering, they use the poles and residues method in the circuit analysis. And also, if you take the differential equations class, you use poles and residues in the Laplace transform methods that are used in solving those. So what I'm doing today is more trying to prepare you to take other people's classes later. You will not really find anything about poles and residues in the book because you can do partial fractions other ways. And so anyway, if you look at something like the first problem in 8.4, they start with this fraction. And what you want to do is rewrite it as a sum of fractions which would have exactly one of these factors in each fraction as the denominators. The reason for doing this from the standpoint of this book and this class is then that if you can find the correct numbers here for A and B so that this would be an identity, then if you were trying to integrate this, you could say it's this integral plus this one. And you can see that these integrals, where A and B are constant, are natural logarithms, because dx, say you think of the A factored out, and you just have the integral sign, and then dx over x minus 3, the antiderivative for that is log of absolute value of x minus 3, or simply log x minus 3 if you're assuming x is bigger than 3. And the same would be true here. Think of factoring out b, whatever number it is, and think of dx over x minus 2, and then the antiderivative is log x minus 2. So the fractions where each one has a single factor in its denominator are what we call partial fractions, because if you get the correct numbers, they'll add together to give you this fraction. Okay, so partial fractions is something that a graphing calculator will do, and certainly something like Maple, Mathematica, MATLAB, and all of that. It's really, as far as just taking a fraction and writing it in partial fractions, that much really is algebra and isn't calculus until you put the integral sign on. So the way that they're selling in the book is perfectly true as far as it goes, and that is that this is supposed to be an identity when you get the correct numbers for A and B, true for all x other than where you'd be trying to divide by 0. So true for any x except 2 or 3. So therefore, you could choose a value, whatever x you like, other than 2 or 3, where you'd be dividing by 0, put that number here, and there, and there, and there, and there, and that gets you an equation with two unknowns, the A and the B, that you need to identify the partial fraction. Then you can take any other x beside the one you used, m2 or 3, put that in, and you get a second equation in the two unknowns, A and B, and then you can solve two equations and two unknowns. Well, that's certainly easy enough to understand, and that's what the book's selling. The only thing wrong with that is that it's fine as long as you're talking two factors and two fractions and two unknowns. Well, how about if you have three factors? Well, then you've got three equations and three unknowns. Well, that's harder. You can do it, but that's harder. But how about 4, 5, so on? That's not very good. If you have enough factors, it's beyond, well, 5 is about all your graphic calculator will handle, is about 5 equations and 5 unknowns. You get enough factors and you're beyond what a really good computer will do. However, the poles and residues method will work no matter how many factors you have, and isn't that hard to do. So that's why I'm trying to show you about it. Now, I won't do anything to force you to use poles and residues. I won't have a test where it would insist that you do something that way. But it is worth your while to get the idea, I think. So, we need a couple of definitions. What's a pole and what's a residue? And this terminology goes back to Cauchy, as I said and showed you with the handout. Cauchy was the French mathematician who coined these words and pioneered this method. Okay, so thinking of trying to find A here. The pole for A is the number for which the denominator is 0. So the pole for A is 3, and the pole for B is 2. It's the solution then that you get if you set the denominator equal to 0 and solve for x. So that's not hard to see. Okay, what's the residue? Well, to get A, what you do is say, as I have over here, why do poles and residues work? Say you're trying to get A, thinking of this same problem, multiply through everything by the denominator, as I did with the green colored factor. So when you do, you see the factor over here in the original fraction corresponding to the denominator of A will cancel out, and it will cancel here. So what it will leave you here is what you call a residue. The word residue in English means what's left over after something or other, right? And so the residue, if you're trying to get A, is what's left of this fraction, the original, after you've multiplied through by the denominator of A. So this is the residue, and it equals A plus the residue times all the remaining terms over here, no matter how many there might be. In this problem, there's just the one term, but you could have 50 terms if they're all fractions like these with different factors over here as their denominator. So you'll have the original denominator of A times however many terms there are. So then, when x is takes the value that is what we call the pole. In other words, when x is 3, you'll have 0 times all this, and it leaves you a equal to the value here at the pole, at 3. So the limit of the residue here as x approaches 3 will be a times the limit as x approaches 3 of x minus 3 times everything. So that's gone, and a equals this with a 3 put in, 15 minus 13 over 3 minus 2, which is what I've said here. A is the residue at the pole, so it's this fraction evaluated at 3, so it is 2. Now what I found is A, regardless of finding B or not. So what poles and residues lets you do is get the numerators of these partial fractions one fraction at a time. Whether you want the others or don't want them doesn't matter. If you do, you can repeat the game and get B, and if there were more factors and more fractions, you just keep going. So in principle, you could do this even if you had a large number of different linear factors like this. This is what you call distinct because the numbers here are different. Linear because they're first power factors. So we can get the pole of B then as 2. The residue is what's left if you have multiplied by x minus 2, so it's 5x minus 13 over x minus 3. People use the word suppress they would say that the residue for A, you identify the factor that's the denominator of A and cover that up like that. The residue is what you see. And then if you want the residue for B, cover that one up. And the residue is what you see. You can look at it that way if you want. And so pole B is 2, and the residue is what I have here, and then B is the value of the residue at the pole, so it's 3. So you can check. See, I'm saying now that 2 over x minus 3 plus 3 over x minus 2, if I add the fractions, will give me what I started with. So when you are trying to add or subtract 2 fractions, just cross multiply. So this times that, whatever the sign is, this times that, and then the denominator is the product of that one. That's math 25, right? And if you do this and do your algebra, you'll see it works. So obviously then, as I already said, the relation to section 8.4, or I guess it's 8.5 in the new book, is that if you put an integral sign on the original problem, you can do that on the partial fractions, and then this one will be, you would have 2 times log x minus 3, and here you'd have 3 times log x minus 2. So I forgot to write the 2 and the 3, didn't I? Well, so you really would have 2 times it, or it would be square, and you'd have 3 times it here, or it would be cubed, like that. So again, as on why do poles and residues work, looking at it one more time, if you wanted A, you could multiply everything by the denominator of A and cancel over here, and when you do, you see what's left is your residue. That'll equal A, and then the denominator of A times everything else. And when you take your limits, here you'll get the 15 minus 13, so you get the 2 equals A, and here you get 0. And then in the same way for B, if you wanted it multiplied by x minus 2, and what remains here is the residue, and you'd have the x minus 2 times A, so, and then you'd have B. So at x equal 2, this will be gone, and the value here at 2 will give you the 10 minus 13 over the 2 minus 3, so you'll have minus 3 over minus 1, which would give you the 3. So for distinct linear factors, poles and residues is really pretty slick. If you have something else, you might have some linear factors repeated. You might have some distinct linear factors, and you might have quadratic factors. It's possible to prove in algebra that you can write any polynomial as a product of linear factors, possibly repeated, and quadratic factors. So everything that you would have to deal with is either linear repeated, quadratic, conceivably quadratic factors repeated. And so you can attack any of the situations with poles and residues. It may be, especially if you get the quadratic factors, as we will do here in a few minutes, you may feel that it's more trouble to work with complex numbers than it's worth. But at least for the linear factors, do that much with poles and residues and cut down how many simultaneous equations you have to solve if you're going to do it in a method that uses solving simultaneous equations to some extent. At least cut down how many variables. So I would say at least do poles and residues like this for the distinct linear factors, because that's pretty easy. And it's a lot easier to solve 2 equations and 2 unknowns than it is to solve 3 equations and 3 unknowns, or 4 equations and 4 unknowns, and so on. At least if you're doing it by hand. Now, if you're using machinery, it doesn't make any difference. It's just electricity. Okay. So, for instance, look at problem 3, where you have a repeated linear factor, as you see. When you have that, you have to allow for whatever is the linear factor to all possible whole number powers up to and including the one that appears in your original problem. So if this is squared, then there can be a fraction with x plus 1 that's first power and a fraction with x plus 1 that's squared. You'll see that that's true because we'll find the A and the B And we'll end up seeing down here that the fractions that will add to give you this are here. There's a fraction with x plus 1, and there's another fraction with x plus 1 squared. So at the very least, I would start doing poles and residues. And you see, if you were doing the equivalent of what I was showing you here with why do poles and residues work, the idea is that to find these numerator coefficients, the a and the b, you multiply through by the denominator. Okay, so the question here is multiplying through by the denominator. Do you multiply through by x plus 1, or do you multiply through by x plus 1 squared? The answer is you multiply through by the repeated linear factor to whatever is the highest power you have it in the original problem. So in this one, you have x plus 1 squared, so that's what you multiply by. And so what you're going to get then is the residue for b, and you think of the minus 1, where this factor is 0, as the pole for b. If this had been cubed, you'd have an a over x plus 1, a b over x plus 1 squared, and a c over x plus 1 cubed. And then you'd be after c to start out, and you'd be multiplying through by the factor cubed, and so on. So my residue for b, if I've multiplied by the x plus 1 squared, is the x plus 1 squared times the fraction here, so it's x plus 4. And my pole b is minus 1, so b is just like in this first problem, the residue at the pole. So you take your residue, x plus 4, put in your minus 1, and you get 3. So b is going to be 3, no matter what else you do. Now, to get a, then, if you want to kind of mix poles and residues with what the book's selling, which is always substitute for x and solve an equation for your numerator of your partial fraction as an unknown. Once you found that b is 3, you could take any x other than minus 1 and put it here and there and solve for a. For example, if you wanted to use x equals 0, which I did, you see, I've shown you if you use x equals 0, where it would go. And then what do you have? 4 equals a plus 3, so a would be 1. So that's a mix of poles and residues and substitution. But you can check that 1 for a and 3 for b work, because if you take 1 over x plus 1 plus 3 over x plus 1 squared, what you'll have then is these two fractions, and if you add the fractions, you see, if you get a common denominator, you're multiplying top and bottom here by x plus 1, and so then you'd have x plus 1 plus 3 and x plus 1 squared, and you see that's x plus 4 over x plus 1 squared. So you can see it works. Now, if you want to do it all by poles and residues, you'd start out the way we did, where we found that B is 3. So then if you were looking at this line, you could do this. Multiply by x plus 1 square, and so then you'd have x plus 4 equals a times x plus 1 plus the b, which is the same as 3. Whether you wrote b here or wrote 3 here wouldn't matter. Because what you could do is you could differentiate. You notice this was your original residue, x plus 4. So the derivative of the residue for b, which you see is 1, would be the derivative here, which would be the a. If you're thinking of this as x plus 1 to the first power, when you do the derivative, you'd have 1 x plus 1 to the 0 power, so it's gone. So you really have the derivative of your residue equals a plus the derivative of b, which will be 0. Whether you just called it b or called it 3 wouldn't matter. So there is a formula then that if you have a repeated linear factor, and it's repeated just the one time, so it's square, then you go for what would be the numerator of the partial fraction that has the highest power first by getting its residue, and then the derivative of the residue will be the numerator for the first power term. There's a pattern to it, so I'd write the derivative of the residue over 1 factorial. The reason for putting in the 1 factorial is that if this were cubed and you had 3 terms, you'd get your residue. Then for the square term, it would be the derivative over the 1 factorial, and then for the first power term, it would be the second derivative over 2 factorial. So you can do it like that. We don't have any problems where there are cubes on the repeated factors, so, but I at least want to say what it is you do. Okay, so what we have with the original problem, if you were going to do an integral, then is the integral of dx over x plus 1, because a is 1, plus the integral of b, which would be the 3, x plus 2 to the minus 2 power. So I've got to put my 3 in there. See, we found that a is 1 and that b is 3. And so then you, with the minus 2 exponent, you add 1 and divide by the new exponent, and so you'll have minus 3. Oh, that one is very good. Yeah. You'd have minus 3 over x plus 1. So now look at, now let me give you some maple on this. For partial fractions, comma, x. Maple demands that you say specifically what letter it is that is supposed to be your variable. The reason for that is that this way, you, instead of having number coefficients, you might have A and B letters, and this would, and a variable that's X, and then this would give you partial fractions using the letters as your coefficients. And you see the 3 over X minus 2 plus 2 over X minus 3 that we did working by hand. And so then if you look, say at problem 3 that we just did, convert X plus 4 over X plus 1 square, par frac. And you see the 3 over X plus 1 square plus 1 over X plus 1. Your graphing calculators will, well, I guess I can't say for sure that all will, but most of them will do partial fractions. If you have one, you can see whether it wants to do them or not. Meanwhile, look at something like 21, where you have quadratic factors. I was saying that in algebra, you can take any polynomial and you can factor it down to a product of linear and what we call irreducible quadratic factors. This is irreducible in that if you were trying to factor this, you'd be involved with the square root of minus 1 with I. The use of the letter I for the square root of minus 1 goes back to Euler, in case you're interested in history of mathematics. He's the one that said we'll use I. The electrical engineers, of course, wish he had said J, but we weren't doing electricity in Euler's time, other than Benjamin Franklin out trying to electrocute himself with the kite and the key, and so on. So, notice also this one is a definite integral. So what we have, you see, if you have a linear factor, you'll have A over the linear factor. And for each quadratic factor, you can have 2 terms in your numerator in general. Some unknown letter B times X, which you notice is a degree lower in power than the denominator, and then the C over X squared plus 1. So what I'm saying then is that for this problem, there are 3 numbers, A, B, and C, where A over X plus 1, BX over X squared plus 1, and C over X squared plus 1 will add to give you this fraction. You could write this part as 2 separate fractions so that there'd be 3 altogether, or you can do it this way, which is what I'm more familiar with doing, and it's what the book's doing. So regardless of what you're going to do or not do to get B and C, I would say at least get your A with poles and residues, so that if you are going to solve simultaneous equations for B and C, you're only doing 2 equations and 2 unknowns instead of 3 equations and 3 unknowns. So for the A, then, multiply by its denominator to get your residue, and where its denominator is 0, which is at minus 1, is its pole. You do poles and residues for each linear factor, exactly like here, regardless of whether you have quadratic factors or not, and regardless of whether you have repeated linear factors or not. So if you were, in other words, to multiply through by x plus 1, over here it would cancel, and what you see is your residue, 1 over x squared plus 1. The pole is at minus 1, so put that in, and you get a half. So A is a half, no matter what you do or don't do to get B and C. So now the most you'll have to do is 2 equations and 2 unknowns for B and C if you're going to follow the book, where they would say find any x you want other than minus 1, because you can't divide by 0, and put in 2 different values for x. Notice you'll also have to put whatever you chose there, and you can solve for B and C. Actually, you see, pretty easy would be to use x equals 0, because then the B is gone and you're just solving for C. So you could do that. Use poles and residues to get that A is a half. So then you have a half to put there. Then if you put 0 in, that removes the B from that equation. The only unknown will be the C, and then you'd have 0 there, and 0 there, there, and there. So you could do that. And then if you know A and C, take some other number like 1 and put that in for x, and you can get to B. So you could do it that way pretty easy. Or you can do this with poles and residues, because if you're trying to get bx plus c, so you have to work with it together, because it's the one denominator, multiply through by that denominator, which will give you, when you cancel over here, what you see as your residue, 1 over x plus 1. So the residue would be this, and you see your pole would be what makes that denominator 0, which is I, square root of minus 1, right? And so your residue is this, and your pole is I. So your residue at your pole removes this, because you've multiplied through really by this denominator when you got your residue. So you have A times 0, and then over here you have bx plus c at I. So this will get you B and C together. The only price that you pay is that you're working with complex numbers. This is why you took Math 108, learned to work with complex numbers, then did some more in Math 143 or 147. So put the I in here, and you have 1 over 1 plus I. Put the I there, and you have BI plus C. So to match complex numbers, they both have to be in what you call standard form in Math 108, which means that you don't have the I in the denominator. You have a real denominator. So if you have this kind of thing, if you remember your Math 108, what you do is multiply top and bottom by the conjugate. Remember, the conjugate has the same terms with the opposite sign in the middle. So I multiply top and bottom by the conjugate, then I multiply these two. The product conjugates gives you real numbers. You have this times this, which is the 1 square, and then this times that, which is minus I squared. I squared is minus 1, so you have minus minus 1, so you have 2. So finally, what this is, denominator 2, you have a half minus a half I equals the real number C plus the real number B times I. So then you match the real coefficients, so C is a half, and you match the imaginary coefficients. Okay? This is all Math 108 or Math 143. It's just that you probably kind of forgotten it. But you can get your two unknowns that way by matching up complex numbers, or you can do substitutions, whichever you want to do. So finally, we have C and B. So then the original integral is the half over x plus 1, and then the 1/2 for the C over x squared plus 1, and the minus 1/2 for the B over x squared plus 1. And the B is times x. So you have 3 terms. So this first one is going to give you a half log x plus 1. This next one, what I've done, you see I have x squared plus 1. If I'm going to call that u, then I want 2x dx for my du. So I've multiplied and divided by a 2. That's this 2 and that one. So that if this is u, that's du. So the integral is going to be this minus 1/4 log x squared plus 1. And then for the third term, I have the 1 over x squared plus 1 squared, and that'll be arctangent. So I have my half log, my 1/4 log x squared plus 1, and I have half arctangent. So this integral with the 2x, as I made it, over x squared plus 1, is really a u substitution problem, but rather than writing it with u and changing my limits, I just figured out that it would be the log x squared plus 1 and left the original variable in the original limits, so that these all match. And so then I have a half log 2 minus a 1/4 log 2 from here, and a half the arctangent 1 is pi over 4. And then log 1 is 0, log 1 is 0, and arctangent of 0 is 0. So then you clean this up and you get what the book has. Let's see, I'm not sure. Did we do 21 with the maple? Turn the page to see. No, I did 22, but and I did 18. I didn't do 21. But so before we go on to 22, is there any question here on 21? This is still all chapter 6 stuff, so the chapter 8 stuff that we're doing will be on test 3. Meanwhile, let's take a look at problem 22. This one is also the quadratic denominator. You can factor this, of course, and you'll have t and t squared plus 1. And so another thing that you can do, you don't necessarily have to do it the way that I have done it here. If you notice, the derivative of t cubed is the 3t squared. And the derivative of t would be 1. So you could split the 4 here into 1 plus 3. You could rewrite this 3t squared plus t plus 3 plus 1 if you wanted. And so you could make this into two integrals. The 3t squared and a 1 out of this as a numerator, and this as a denominator. Then if this is u, this is your du, and then that would leave you this t and the other 3 out of the 4 over the original t cubed plus t, which you could write factored. So you could get this integral without worrying about partial fractions, and then worry with the partial fractions for this fraction, t plus 3 over t times t squared plus 1. The advantage of doing that would be that this is first power instead of square, and so your fractions are going to be simpler things to manage. If you were going to use maple, you wouldn't bother with all that, because if you use maple, you can just say convert par frac for the original problem, or you could get maple to do the integral, type int, and be done with it as far as that goes. Come up with the number. You notice this thing is a definite integral. So what I've done then is to split the problem, and this first part, 3t squared plus 1 dt over t cubed plus t, is du over u. So I've gone ahead and done my du over u part. See, I get limits on u because it's a definite integral. So when t is 1 and u is t cubed plus t, u would be 2, 1 cubed plus 1. And so I have that down here. And when t is square root 3, and this is the u, I have 3 times square root of 3 out of the cube, and then I have another square root of 3 there, so that's 4 of them. So my limits on u would be 2 to 4 root 3. And so then I get log u, and between the limits, and so that'll be log 4 root 3 minus log 2, and that will give me, remember the difference of the logs is the log of the quotient, so it's log of 4 root 3 over 2, and that's log 2 root 3. So my answer from this first part is log 2 root 3, which I'll eventually be using up here to get the final answer. So I don't want to lose it altogether. Meanwhile, let's work with this part where we would do partial fractions. The point is that this is a simpler fraction to work with than the original. That's what I'm gaining by splitting the problem up this way. I think it's a reasonable way to look at things if you're going to do this by hand. As I've already said, if you're using machinery, then it doesn't make any difference. Just let the machinery do what it will do. Get my sign. So we have the t plus 3 over t times t squared plus 1, which we'll write as a over t, and then bt plus c over t squared plus 1. So once again, then, the a would be the residue. If you thought of multiplying through by the t, your residue would be t plus 3 over t squared plus 1 at your pole 0, which would be 0, and so the a would be 3. And then for the quadratic factor of the original denominator, you would work on the b and the c together with complex numbers if you do poles and residues. So your residue would be the t plus 3 over t, and your pole 0 is I, the same as it was for the other problem I did. So bt plus c at I would be the value of the residue t plus 3 over t at I. So that would be 3 plus I over I. And again, to match this complex number to this one, you have to get standard form. You have to get the real denominator. So the trick is always that you multiply by the conjugate of your denominator. That gets you a positive denominator. So by minus I, because I square is minus 1 and minus I square will be 1. So your c plus bi will be this numerator times minus I, which will be minus I square and minus 3i. So this is 1 minus 3i. So c plus bi is 1 minus 3i. So c is 1 and b is minus 3. So that means then that this part of the problem with the limits 1 to root 3 would be the a, which is 3, dt over t from 1 to root 3. Okay, that's going to be logarithm. And then what you're going to have is minus 3, the bt plus c over t squared plus 1. And so this will split then into two integrals. Okay, so here with this one, you can see that's logarithm. So it's 3 log 1 to root 3. And then what I have done is I've split this one into two parts. I'm looking at the minus 3t over t squared plus 1. I factored the minus 3 out, and I divided and multiplied by a 2 so that I'd finally have a 2t over t squared plus 1. That's kind of the same trick that I did here with this one, where I factored out the 1/2, and then I put in a 2 there and divide it by a 2, so I'd have 2x over x squared plus 1. I've done that here, so I'll have a 2t over t squared plus 1, so that this is natural log of the denominator. If that's u, this is du. But rather than doing it with a formal change of the letter to u and the limits, I just saw that this form will give me the logarithm and stayed with the original limits and the original variable. And then here I have the dt over t squared plus 1, and that's arctangent. So then it's a question of putting in these limits, which is messy, but I think this is what you'll get. And remember that we did part of the problem separately, so that's why the blue pen goes here, finally up here. So we have the log 2 root 3 from the first part, and then we have the, then this part, you see you have log 4 minus the log 2, and so that's over here, log of 4 over 2, and the minus 3 halves. And then we have the 3 log root 3 from this first integral, which is there. So this integral is there, and is finally here. And then this one is this part, and that's finally here. And then the arctangents give you pi over 3 minus pi over 4, which is pi over 12. And so if you mess with the logarithms enough, you can get these steps and finally get to what the book has. This is all kind of messy, but it'll go. And so notice if you look at the maple, that we are on the back, where I say some denominators have irreducible quadratic factors. We have the convert par frac. Maple hasn't done the problem the way that I did, and it may be that it's better not to have, but anyway, in partial fractions you have number 9. Then if you want to integrate the original one, you see answer 10, and if you take the 2 logs that are in Maple's answer, you can match that up with this. You see, because your 2 log 3 is log 3 square, which is log 9, and your 1/2 log 2 is log square root 2, and so you have log 9 minus log square root 2, and the difference of the logs is the log of the quotient. So you can reconcile what the book has with formula 10 in the Maple, all right. Okay, so the last one, notice that some of these problems are improper fractions. And if you do with the calculator or Maple, that doesn't matter. If you notice with the Maples convert par frac, it just goes ahead and gives you the x squared plus 1 that you get if you divide this down using log division, and then it gives you partial fractions for the rest of it. So if you're doing this by hand with your improper fraction, first divide it down with long division. So what goes here times what's here brought over here has to be identical to the line above it. And then whatever this is multiplies all the other terms, and you go across. Then you subtract, so you change sign, and you see this, the degree here is still as much as this is, so you have another term. So the 1 times x squared and the 1 times minus 1, and you subtract. So your original fraction is the quotient, x squared plus 1, and then the remaining fraction is 1 over x squared minus 1. So then you do this in partial fractions. It's very much like problem 1, and you can do 2 equations and 2 unknowns. If you really don't like my poles and residues, I don't care. But A would be the residue here, which would be 1 over x plus 1. And then at the pole, that will give you a half. And the B would be the residue at its pole, which will give you minus a half. And you notice then that if you do the partial fractions and check the addition, it works out to give you the 1 over x squared, you see, because the x's cancel and you have 2 over 2, so 1 over x squared minus 1. So however you get them, these are the partial fractions. So the original problem then is your integral of this part and then half integral dx over x minus 1 for the first partial fraction, minus a half dx over x plus 1 for the second partial fraction. And these integrate pretty directly. Here, these are both logarithms, and you could combine these. You have difference, so it's quotient. And then if you want, you can take the half power, and so you can write it like that. So you could write your answer any of these ways. And let's see. If you look at Maple's answer, the 12, it has this, I guess. Well, what we will do next week then, we will talk about how you do definite integrals when you can't get an antiderivative as a function that you know. A function that you know, like the trig functions or sinh and cosh, for example, are what you call tabulated functions, or what you call elementary functions, in that somebody at some time found the appropriate power series and made tables of values which now you could get out of your calculator or computer. So those are what you call closed form solutions. Well, there are a lot of definite integrals where you cannot get a closed form solution, but there still is an area, or whatever the integral represents. So then we have numerical methods, and that's what we'll talk about on Thursday. Simpson's rule and the trapezoidal rule particularly. And then we will talk about what are called improper integrals, where you're working with definite integrals but they go to infinity, or they include a vertical asymptote at an endpoint, something like that. We'll do that sort of thing on Friday. So work on the test and have a good week.